So as we said, discovered previously, we need to relax a little bit the domain consistency, because this one would be a little bit too computational intensive to compute at every call of the propagator. So we will relax a little bit the domain consistency, and we will do something a little bit weaker. We will just try to detect subchains, and we will try to prevent the subtor a little bit lazily. Okay, every time we discover that there is a chain that is created, we will prevent it from closing too early. And so assume that we have this situation here. We define a subchain as a consecutive sequence of nodes with a unique successor. So the question here is, how many subchains do we have here? Example. The answer is given here. You can see that there is one subchain that is represented in yellow. Okay, you see that here I've got one single successor, one single, and so you create a subchain, and then the subchain stops here because there are more than one successor. Then there is another subchain here, which is represented in blue. You see that 7 has only one possible successor, and we also have the red subchain. And what we mean by closing, preventing to close the subchain too early is that we can remove this edge. Okay, so it's quite clear that we should not be able to assign to the variable 6, we be able to assign as a successor the variable 0, the node 0, because otherwise we would create a subchain, and this is not allowed by the definition of the circuit constraint. Same here, we would like to remove this one, and we would like to remove this one. So every time we discover that the subchain has less than n-1 edges, we cannot close it too early. The question is, how do we solve this efficiently for n variables? We need some data structure that we will maintain during the search to do this efficiently. And actually, we will maintain 3 destinations for every node. We maintain for every node the destination of the subchain. Okay, starting in node I, what is the destination of the subchain? If the node is not bound, we will assume that there is a self loop, and we will say that the destination of node I is I itself. Then we can also be interested to discover the origin of the subchain passing through I. Okay, and if the variable I is not bound, of course it will be I as well. Okay, we create a kind of self loop. Then we have also the length to the destination, which is the number of hops or the number of links that you need to go through, starting from I up to the destination, which is here. And so let's see a little bit in example what we have here. Okay, so if I take the node 1, so this node 1 here, the destination of node 1 is 6, because this is the longest subchain that you can create starting from 1 is up to 6, and so the destination of 1 is 6. The origin of node 1 is 0, because the subchain was starting here, and the length to destination here is 3, because you've got starting from 1, you can go through 3 hops, 1, 2, 3, 3 like this, 1, 2, 3. Let's take another one for 12. You see that this one is not in a subchain, so the destination will be 12, and the origin will also be 12. Okay, we assume that there is a loop, and the length to the destination here is considered as 0. What about the node 4? The node 4 is represented here, and you see that it's the destination of 1, which is the blue one. So the origin of 4, this is the interesting thing, the origin of 4 is 7. Okay, the length to destination is 0, because the destination of 4 is 4, this is the end of the subchain, and the origin, as I said, was 0, and so the length to destination is 0 as well. So these are the 3 information that we will maintain in every node, and we can update them efficiently in constant time every time a new edge is assigned inside the graph. So let's assume that if you consider the situation before, as a successor of 6, we had 8 or 7. Let's assume that the branching or by propagation, one of these edges has been removed, okay, or this one, and only one remains. And the one that remains is 6, 8, okay, like this. So now we can extend the subchain. And what is interesting here is that because now we are sure that the successor of 6 is 8, we've got a larger subchain, okay? We will concatenate the subchain, which is the yellow one and the green one, to create a longer subchain, okay, like this one. And so we can do that in constant time, because all we need to do is that to say that the destination of node 0 is not 6 anymore, it is now 14. Okay, we can do that because we knew what was the origin of this yellow subchain. Okay, so we can have it here. And so we will set as the destination of the origin of 6, so the destination of 0 is equal to the destination of node 8, which is 14. So we can update that in constant time. Then we also have the origin of the destination of 8. Okay, so the origin of that one is now 0. Okay, and to do that, we will say that the origin of 8 is equal to the origin of 6. And so in constant time, again, we will have now that the origin of 8 is 0 as well. Then to update the length to the destination from 0 is 8. Okay, and so we can do that with this formula. So the length to the destination from 0 is equal to the length to the destination that we had before. Okay, here, plus the length to the destination of 8, plus 1 because we have added this white edge. Okay, plus 1 here corresponding to this white edge. So we can do that in constant time once a new edge has been detected as added inside the graph. And so the propagate circuit can update all the data structure like this. This is the initialization of all my data structures. So as I said initially, we've got loops, and the length to destination is 0 for all the nodes. Then we will iterate over every node. If we detect that one of the edge is bound, then we have a new subchain. Okay, so one of the edge is bound, which means that we have a situation like this one. Then we will update with the formula that we have seen just before. Okay, we update the destination, the origin, and the length of the origin of I, assuming that this is the edge ij that has been added. Okay, so if the edge ij has been added, we will update the origin of I, we will update the destination to the origin of I, so we will update the destination of that one, and we will also update the length to the destination of the origin of I. Okay, and we will do this check. So if you realize that the length to the destination of the origin of I, so this one, if you realize that the length of this new subchain that we obtained by concatenating the first one and the new one, okay, so we have a concatenation of two subchains. If the length here is less than n minus 1, then we will remove this backward edge to prevent closing the subtour too early. And then we do really here, this is the pruning that we will do inside the propagator. This is where we remove one value from the domain of the variables of the variable x of the destination of j. Okay, we prevent this one from closing too early. Okay, and by construction, so by induction, you can already realize that all these ones, if they needed to be removed, they already have been removed. Okay, so by construction, okay, or by induction, all these one has been removed before. So this is really the only one that we need to remove now, and the subtour of being created. The question is, can we do this a little bit more efficiently? And by efficiently, I mean more incrementally. Really update the data structure only when one given edge has been added. And the answer is yes. You can store all this inside state integers, okay, so that they will be restored on backtrack. And then you can only trigger this code that I have put inside the yellow box. You can make sure that only this code is executed when a new edge, when xi is bound to its new variable, in that case j, to this value j. Okay. And so the time complexity overall will be in the order of the number of bound variables. Okay. And so if you do that incrementally, this will be less than order of n. So this is more efficient, and this is what we mean by an incremental filtering algorithm. And this is what you will implement during the practical session. This is not the only filtering that you can do for the circuit constraint, because you know that the constraint is NP hard, so you could do more filtering or more advanced feasibility check. And one check that you can easily do that would also be polynomial is this one, is check that there is not more than one strongly connected component. And you know that there are some very efficient linear time algorithm to detect the strongly connected components. These algorithms are called, for instance, the one of Tarjan or the one of Kozaraju. Okay. If you call this algorithm and you realize that inside the graph that is defined by the successor and the domain of the successor variables, if you detect that there are more than one strongly connected component, you can already immediately fail, right? Because it means that it's totally impossible to create one single directed circuit in that case. So this is one additional feasibility check that you could do by the one that I just explained before with the subtool elimination by using the chains. So that's it. This closes the circuit constraint filtering algorithm.